Well, hello. Today we are going to be talking about exponential growth and decay functions. Now, we've already talked about continuously compounding interest. And if you recall, we did that previously. That was this formula A equals P e to the RT power. And you'll remember that this was our final amount. If we invest some money, if we were able to find a bank that could compound interest continuously. And R was our interest rate, and we'd write that as a decimal, and T was our time in years. And P was the initial value, the initial investment. Well, if you look, this is actually really close to this formula that we got here. This one looks a little more complicated, but it's really just a function written in function notation. We have the function A, and that's like our final amount, A of t. And then A sub 0 means the amount at time 0, the amount when t equals 0. Then we have e to the kt power, right? Well, notice here that this the t is the same, right? And then here we have this k. This is our growth constant, and that's the same as r. So this formula right here is really the same thing that we were looking at previously when we were talking about continuously compounding interest, except this actually has a little more application. Because while money, it's great to use this formula to make a model, banks don't actually really pay that. I haven't been able to find any that have paid that. However, there are different things we can use an equation like this for to model things that do compound continuously. And if you can think of anything where it's just constantly growing, maybe like people, populations, we're constantly growing. It's not like once a month all the babies are born on the first of the month. It's not, our population isn't compounded monthly, or it's not compounded weekly. Every single Monday every baby is born. No, like the human population is just constantly growing. There's always babies being born. And so what we have, this is a model that's going to work better for something like that. Now, anything that's living and organic and has this type of exponential growth, this is probably a little better formula than something that is compounding annually or compounding monthly. Okay, so before we look at something really big like the human population, let's look at something really, really small, maybe like bacteria. So the first thing to note is that we have this 2 times 10 to the 4th bacteria are in a colony, and then 8 hours later the population is just a little more. I mean, it doesn't look like it's that much more, but it really kind of is, because 2 times 10 to the 4th is 20,000. And then 8 hours later, the population is already at 30,000. So determine the growth constant K. Well, we'll start out by writing our formula. So A of t equals A of 0 e to the kt power. And we can plug in what we know and solve for what we don't. So our final amount is 30,000. So we'll go to that. Our initial amount, the amount at time 0, is 20,000. It says e to the kt power. Well, it says 8 hours right here. And that's pretty important, the fact that this is in hours. We'll come back to that. So 8 is our time, and then we have our k. And it says determine the growth constant k. So now that we have this equation, we just have to actually solve for it. So we will go ahead and divide both sides. If we're trying to isolate that k, we'll divide both sides by 20,000. And we have e to the 8k equals 1.5. So 30,000 divided by 20,000 is just 1.5. Now what we're going to do here is we can, some people call taking the natural log of both sides, or rewriting this in logarithmic form is how I like to think of it. The base is e, so that's like log base e of 1.5 equals 8k. Now this is good, but most people actually don't write it as log base e. By convention, we more often than not will just write it as natural log. So we have natural log 1.5 equals 8k. We'll divide both sides by 8, and now we have to actually solve for this. This is the exact answer, by the way. K equals natural log 1.5 divided by 8. Now let's go to our calculator, and we can get a decimal approximation for that. Okay. So let's check in with our calculator. Let's clear this out. Oops. All right. So we're just going to take the natural log of 1.5, and then we'll divide it by 8. I would like to do that. So we'll just do that, and then divide it by 8. And here we have our decimal approximation. Now, one thing that you'll want to do for this, though, is we're going to actually store this in the calculator. That way we can come back and use it in a little bit. So I'm going to do that. This little arrow right here, we've done this in the past just to store for a variable. So we're going to store, and let's put it in here for, well, you know what? Let's use k, right? Right here's k. So we'll store it for alpha k. There. Now, anytime I use k, it will use this number instead. But as is, I can approximate it right here, and we get 0.051 is what that would round to. So 0.051. There's our constant k, and that's what we wanted to do. So, all right. What's the population 2 hours after the experiment starts? All right, well, once again, we can think about this for a second. 8 hours later, it'll be at 30,000. We started with 20,000. So right away, we know we should get a number somewhere between 20 and 30,000, right? So all this is using our function notation. Oh, you know what? We're going to actually put in 2 for t. So we'll put a of 2 equals our initial value, 20,000, e to the k, which is this, so approximately 0.051. And I'm going to use that long decimal that we have. We already have that stored in the calculator. 0.051, and then times 2. Okay, so back in the calculator, I'm going to take 20,000, and then we'll do, I usually like to do times. You don't have to. You can just put the e right in there. We'll do e to the alpha k times 2. Now, if I were to just put this in here, this actually isn't going to give me the right answer. And that's because your calculator is going to do order of operations. Remember, we've got to do e to the, we got to put a parentheses around this. Now, if you have a little bit nicer calculator, if you have one that will do the math type a little bit better, if you're rocking the Casio Prism or the CG50 or one of the nicer TIs, you don't have to worry about that. You just throw that up there. But this one, I got to make sure to pay attention to my parentheses because of the calculator does do PEMDAS. And this right here is going to be my answer for the population after 2 hours. Okay. So that was 22,133. And then we do know that, this, if we're just estimating, it'd be like 0.638. But as far as bacteria goes, we'll just I'll call it good right there. The last part of this problem says, how long will it take for the population to triple? If we're looking for a tripling time, then let's think about what it was at the start. We know our population started with 20,000, and so we can say 20,000 e to the, we'll use that same 0.051, and we're trying to solve for time. That's what we don't know, so we'll leave t there. And if we're trying to figure out when it triples, I'll just take 20,000 and triple it to 60,000. Now, truth be told, these numbers don't really matter because, as you can see, when we divide them out, it's always going to be 3. If we're looking for the tripling time, we're always going to have the left side, after you do a little bit of simplifying, 3 equals e to the 0.051 t. And then from there, once again, we'll rewrite this in logarithmic form, or as I said, some people say take the natural log of both sides, right? And then we have natural log of 3 equals 0.051t. And then we'll divide both sides by 0.051. And we'll go back to our calculator then. And the same thing as before. I'm actually going to take the natural log of 3. This time we'll just put it all in one go. So natural log of 3 divided by, and then remember I have that 0.051. I have that stored in as k. So that gets me my 21.676. And then we got to think about this. Is it days? Is it hours? Years? Well, a lot of times in these exponentials we think about it in terms of years. But remember what we highlighted at the very beginning of the problem. 8 hours. You see, our time is in hours. So this is 21.676 hours. Okay. All right, now you might say to yourself, man, when am I ever going to use this? Like, I don't care about bacteria. Well, you know, lately, and depends on when you're watching this, I guess, we've had a lot of problems with different viruses. You know, right now, as I'm recording this, we have an issue with the coronavirus happening. But it wasn't that long ago that we were dealing with an Ebola outbreak. And just before that, we had a SARS outbreak. And so viruses are another thing. They're living, I don't know if you call them organisms, but they're living, and so they tend to spread in an exponential way, at least for a while. You know, it's a good thing that they're not just straight exponential, because then we're going to all end up with Ebola or SARS. And so eventually that curves off, and we can use a different model for it. But for now, let's create an exponential growth model for the spread of this coronavirus. So on January 19th, Johns Hopkins had confirmed 278 cases. So in other words, our initial value is 278. And then we'll use e to the k, t equals the final amount. As we keep reading, it says by January 30th, there were approximately 11,200 cases. Okay, so that means that we can put some numbers in here, and we'll say 11,200 cases equals 278 e to the k, and then what we'll do is we can say that this is going to be 11 days later. So we're going to let this be the initial amount, and so this is pretty easy to just subtract those. We get 11 days. We'll divide both sides by 278, and then we'll take the natural log, or rewrite this in logarithmic form. And let's go ahead and take a look at this here. So we're going to have 11,200, whoops, one too many, divided by 278 equals 40.2877. Right, so I'm going to just approximate that. And that's equal to e to the 11k power. We'll take the natural log of both sides, right? And then we'll have 11k equals natural log 40.287, and then we divide both sides by 11. This is going to get us our growth constant. This is going to get us how fast the virus is spreading. So let's go back to our calculator, and now I'm going to take the natural log of that number. So I'm going to use my answer key. Okay, so remember this is temporarily stored in answer, so we just hit natural log answer. and then we'll divide that by 11. Okay, so this number right here, 0.3360, is our K value. So K equals 0.336. That's pretty close. You can store it if you want, but it was 3360. So what this means is that our virus, the infected population, is growing by 33% each day. If we're to believe that this is an exponential model, it's growing by 33% each day. That means that roughly about every 3 days, the population is going to double. Okay, and I know that you've studied the power of doubling previously. When things double, and if it keeps going that way for a very long time, that's very, very powerful. So we can create an exponential model here. So the first one, then, we would just say like A of t equals the initial amount, 278, e to the 0.336t. So here's the answer to our first question. Right? Create an exponential model. Use your model to estimate the number of cases on January 25th. So all we've got to do here is, if we want January 25th, we're going to say A of, and let's see, that's going to be 25 minus 19, so that's 6 days. So we can say 278 e to the 0.336 times 6. Okay. And so we'll go in here to our calculator. We have, let's bring it over here a little bit. We've got 278 times e raised to the 0.336 times 6. And it is a good idea to store these variables, but I can see that this one's so small it's not really going to matter. Now that means that we were predicted to have 2,087 after 6 days. Now, interestingly enough, we can actually go back and check how many confirmed cases we did have after 6 days. I found a little website here that we can go check out. This was, let me show you the web address here. There we go. So this is a little website that just has the confirmed cases by Johns Hopkins, and there was more here. You can see that on the 19th there was 278 cases. And if we come over here to the 25th, you can see that it says about 2.7K. So a little bit more than what we had. And if we check on the 30th, which was the one we used, or no, I'm sorry, here we go. 30th, you can see that it was 11.2, or about 11,200. And this is definitely some kind of an exponential model. You can see it's growing much quicker than a linear model, and we might use some other regression for it. Maybe you can find a better fit, but typically for growing things that are alive like this, we want to use an exponential growth model that's continuously compounding. Now let's do one more thing. We've got one more that it says predict the number of cases on February 3rd. So February 3rd will be 15 days after the start. Now this is called extrapolation because now we're actually going outside of the boundaries of what we know. We know that on the 19th we had 278 cases. We know that on the 30th we had 11,200 cases. And so once we go beyond that, now we're trying to make a prediction. Like our graph kind of looks like this, and what we're trying to do is to figure out what's going to happen over here, over further to the right. Okay, so we can do that, and you know what? Let's actually go to the calculator, And all we've got to do is plug a 15 in, but we're going to actually go to the graph. We haven't done much with the graphing yet. So just as a little refresher, we can go over here. Let's see what I've got. Oh, look, I even have it in here from when I was working this out earlier. So 278 e raised to the 0.0336, yada, yada, right? And if I hit enter, I've got that. Now I've already adjusted my window, but as a reminder, you might need to adjust your window. We only need to go out to 15 days, so I have my x min at 0 and my x max at 20. I set my y min down here at negative 10,000 just because it frames it a little bit better. And then I put my max up at 100,000. I think that's plenty good for what we need. Okay, and if we want to know what it is after 15 days, all we have to do is hit trace, and we'll put in 15. So this puts it in for us, and it tells us that we're expected to have 42,945 cases after 15 days. Well, let's see how we did. Let's go back to here, and let's find February. Let's see here. No. February 3rd is 23,000 cases. So our model is off quite a bit right now. And you know what? That's okay, because it's just a model. And remember, we were making a prediction based on data over here. It was hard telling exactly what's going to happen. But that was the model that we used, and our prediction was off a little bit. Now, it doesn't mean that we should never use these models. It just means that, hey, that happens. It happens when you're making predictions about the future. I realize this, tongue-in-cheek. This is in the past, but based on the information we had, the information we were given, which was only the 30th, from the 19th to the 30th, and now I want you to make a prediction somewhere out here, well, that's also one of the reasons why it's really dangerous to make predictions that are very far outside of your data. Okay, and again, that's called extrapolation. All right, let's keep going here with some more practice. The countries of Georgia and Tajikistan, they're both former members of the Soviet Union, had the same populations of 5.5 million back in 1992. However, the relative growth rate for Georgia was 0.9% per year, and Tajikistan was 3.2%. So one of these countries is growing much, much faster than the other country, right? So it says, in what year might the population of Georgia reach 10 million? Well, what we're going to do is we're going to take the initial starting value for Georgia, which was 5.5 million, and I'm just going to leave this as 5.5. I'm not going to put a whole bunch of zeros on there. We just know that it's a label, right? And then we have e to the, all right, so Georgia is this. Now, 0.9%. Remember, if this is 1%, it'd be 0.01, but it's even less than that, right? This 0.9%, we've got to move that decimal 2 times. So it'll be 0.009 is what that one will be. So this will be 0.009 t. And we want to know when this will be 10 million. So we'll just set that equal to 10. And then we got to go ahead and solve. Now, there's a bunch of ways of doing this. What we've been doing so far is to divide both sides by 5.5. And then we have, and then we'll take the natural log of both sides, or rewrite it, and we'll solve that way. So natural log of 10 divided by 5.5 equals 0.009 t, and then you divide both sides. So that'll work. We can also graph this one as well. That would be just fine too. Let's go ahead and use our graphing calculator a little bit more, and this time we'll go back into graph. And let's clear this out because we're done with this. So delete that. And this time, you know what I'm going to do this time is I'm just going to graph this as two different equations. 5.5 e to the parentheses 0.009x. And so that's one of them. And then for the other one, we'll just graph this at 10. Now this is a pretty slow growth rate. So we want to know how long until this, just about pretty much how long until it doubles. Okay? So if we graph this, probably not going to see much. And here's why. My window. I'm going to let my x-min be 0, and and my y-min, I'm going to, this is going to take a long time for this to double. Like, that's a really low growth rate. So why don't I put this out at like 100? Let's see if it'll double in 100 years. Okay. And then the other numbers that I need to change then, of course, are my y-min and my y-max. I can set my y-min at 0 and my y-max. Remember, we're only trying to get to 10, so how about I just set it to 11? And we'll draw. Hey, look at that. That was a guess. That's just no understanding this and realizing what's happening. You can see they cross right here. And if I do gsolve intersect, then it tells me that it's 66.4263 years. That's how long this is going to take. So we've got 66.426 years. Now, the thing is, that's not the actual answer. If you were to write this on a test, that would be wrong. And if somebody asks you this question, hey, in what year? Well, you've got to pay attention to that. It's not the 66th year. It's 66 years from now, or really from 1992, I should say. So what we've got to do then is take 1992 plus the 66.426 years. We don't need no calculator for this, right? We can handle that. So sometime during the year 2058, that is when this happens. That's when our population will reach 10 million. Well, it's probably not going to happen. But that's a long ways out. Remember how far off we got with our growth model with bacteria just on a couple days? Imagine being 50-some years or 66 years in the future and trying to predict what will happen. So these models tend to break down once you get outside of your realm very far, outside of your working domain. All right, what will the population of Tajikistan be when Georgia's population hits 10 million? Well, we know that Tajikistan also started with 5.5 e to the, we're going to use this time 0.032, and we'll use the time value, which is 66.426 years. Okay? And you put that in your calculator, and I'm going to save you a little bit of time and just write it out here, but you should check that out. That's 46.081 million people. Okay, or about 46 million. You could even just round that there. So while they both had the same population in 1992, 66 years from now, Tajikistan is predicted to have way more people. All right. Okay, the next thing we're going to look at is something called half-life. Half-life just means how long does it take in order for you to only have half of the substance left. And in this case, this is a radioactive material, polonium-210. And it has a half-life of 138.4 days. So every 138.4 days, you will have half of it left. If you start with 0.4 grams, then after 138.4 days, you're only going to have 0.2 grams. You're only going to have half of it. right? And after another 138.4 days, you're going to have even half of that. And you're going to have half of that. You see, what this is saying is every 138 days, you will only have half of what you started with. And so if you think about this, we've got 1, 2, 3, 4 halvings. And that's kind of like saying just start with 0.4 and let's multiply it by a half 4 times, right? Because we would have 4 halvings in order to get there. And then if we go and we take, let's get this out of the way. That's right in the way there. Let's just do a quick double check and confirm. We can do 0.4, and then we'll do raised to the 0.5, well, no, 0.4 times 0.5 raised to the 4th power. And we get 0.025, and that's just exactly what we thought we would get. Right? So, yeah, half-lives, that's just mean, like, it's for things that are decaying very slowly, usually. I mean, it's just kind of become the standard for anything now to talk about its half-life. Okay. There's a couple formulas we can use for this, and we'll reference these as we progress throughout the rest of this lesson. I know we've got about 3 more problems to go, so it's a little bit longer one. But we've got the formula we've been working with here. And this K right here, that is this K. Okay? Well, it's just because if we're talking about half-life, we're going to be dealing with 1/2. So let's take a look at where these other formulas come from, though. So if I were to start out with, why don't I start out with like 1 unit, I don't know, whatever it is, and that will be my initial value, and I want to know how long until I only have half of that left. And so if I want, I could then rewrite this in a logarithmic form or take the natural log of both sides. Right? And then I get kt. And then if I go through and if I were to divide both sides by t, remember, we're trying to find the half-life, right? Or something related to the half-life. So t is actually half-life in this. And so it is an amount of time, but that's why we have k equal to 1/2, natural log 1/2 over t. K equals natural log 1/2 over half-life. That's not half minus life, that's half-life. And so that is an amount of time. That's where that formula comes from. And then of course back over here with this one here, if we were to take that and instead of dividing by t, there it is. Instead of dividing by t, if we just come back and divide by k, then what we're going to get is t isolated. Those cancel out, and I get t equal to natural log 1/2 over k. And that's this other one. So that's where these other smaller formulas come from, and we'll kind of be using those as we progress through here. So let's take a look at just a couple more. A certain radioactive isotope has a half-life of 32,000 years. Right? The decay rate on that is just such a small number, and so it's maybe a little easier to talk about in terms of a half-life. If there were 12 grams of the isotope remaining after 43,500 years, how many grams were there initially? So we want to know about the initial amount. Remember, we can do a couple different things. One, we can use this formula that we've been working with. It's a nice little formula. Right? And we're just going to try to solve for the initial amount. So if we put the 12 in for this final amount, and we'll leave this one as the initial amount because that's what we don't know, and then e to the kt. Okay, well, the k, that's actually something that we were working with just a minute ago, right? Remember, we know what k is. K is this whole thing. So we could use that right here, and I could say, well, k is actually equal to the natural log of 1/2 divided by half-life, 32,000 years. Okay. And then we also know the time. The time is 43,500 years. And this goes in here for k, so we can put that. You could write k right here. I'm going to go ahead and write it. So natural log 1/2 over 32,000. Whew. That's kind of ugly looking, right? And then what we'll do is we'll divide both sides by e to this power. Okay, and then we should end up getting. Let's check this out here. And here's what we get in the calculator. You can see I did e to the 43,500 power times natural log 1/2 divided by 32. And then we took that and did 12 divided by that. Like that's kind of gross, but it works. So we get 30.789 and that's going to be grams. Okay. This is how many grams were there initially? There were 30.789 grams. And if you consider this, the half-life is 32,000, which means every 32,000 years you'll end up with half of this. So a little more than 1/2 happened. So I want to talk briefly about another way to think about this problem. We know if we're talking about half-lives, and it says there's 12 grams remaining, that's like a final amount. And we don't know the initial amount, so I'll still just use a sub 0. And what's going to happen here is we're going to take this number and we're going to be multiplying it by 1/2 over and over and over again. Because that's what half-lives do. Like remember back here we said, on this one we said we're really just taking it times 1/2, times 1/2, times 1/2. That's what a half-life is. And when we found out that we were doing that 4 times, we could say 1/2 to the 4th power. So in this case, though, we need to know how many times we're multiplying this by 1/2. So I'll say 1/2, and then 43,500 over 32,000. That's how many halvings are going to happen. And if you look at this, it's really going to, it comes out to be a little bit more than 1. It comes out to be 1.39375. So a little more than 1 halving happened. And the reason why I like this is just kind of a little bit cleaner even to put in the calculator, right? Because we can do 0.5 raised to the 43,500 divided by 32,000. And then we'll take 12 divided by that. And it's just a little bit cleaner to do. We still get the exact same answer of 30.789 grams. Okay. Let's go ahead and take a look at part B. How long until only 1 gram remains? You know what? We can use kind of this little shortcut here. And that's not so bad. We can say 1 equals, because we want to know how long until 1 gram remains. Right? And we'll use this. Okay, so we got our 30.789, and that's going to be 1/2 raised to the I don't know over 32,000. So it looks something like that. And then the first thing that we'll probably want to do is we can divide both sides by 30.789. So we'll divide the left side and the right side by 30.789. Okay. And then we're going to work on probably taking the natural log. And that's just so that we can move that exponent out. So we've got this 1/2 to the t over 32,000. Now, in order to move something out of an exponent, one thing that you can do is to take the natural log of both sides, or rewrite it as base 1/2, but that's, so we'll just do this. And that's going to now move this down to the front so that I get t over 32,000 times natural log 1/2, or 0.5, equals natural log 1 over 30.789. Then we're going to go ahead and divide both sides by natural log 1/2. And then this on the calculator comes out to be about 4.944 equals t over 32,000. Then we'll multiply both sides by a 32,000. And I got 158,218.979 years. Wow, that's a long time relative to my life. So that's the length. Now, there are other ways you could do this problem. In fact, let's just look at this way real quick. Like this one, this all turns out to be really ugly. And like I said, there are other ways besides just what I did. I just wanted to kind of keep doing the same thing that we were doing there. But I do want to show you one other thing that we could do. And that is, let's explore the graph. So if we come back here and we just put these in here, just like what we were doing before, we're going to graph them as maybe two separate equations. You can graph them as one and find where it's equal to 0, but I like the visual of two different equations. So let's take 30. Let me bring this up. So 30.789 times 1/2, I'm just going to use 0.5, raised to the x divided by 32,000. So there's our first equation. And then for the second equation, we want to know when that's equal to just 1. And if we graph, not going to get a lot, right? That's because, remember, we see what our answer is going to be, 158,000. So let's check the window. And it's okay to go from 0, and I'm going to go out to 200,000. This could be done, of course, just with some exploration. There we go. And we don't even need to see, this did start up at 30. I left it at 11 from where it was before. We've got this spot right here. I'll just do gsolve, intersect, ISCT, and you can see that's what we get right there. 158,218,979. Man, that's just exactly what I had. Right, so that's so much faster if you're comfortable using your calculator. All right. Next problem here. Now, I would encourage you really to kind of pause the video right here and try to get going on and figure these out, and then I'll come through and give a brief explanation. But this is a great place to pause it and then hit play if you're stuck. So these are the values that I got for this, and if this is what you got, then you should just start jumping ahead. We got one more problem to do. But I'm going to go through and talk through these briefly and show you how I did them on the calculator as well. So the first thing I did was I solved for the constant k. I said k is equal to this, and I needed to put that in the calculator. So I'm going to come over to my calculator and take natural log of a half, or 0.5, and then I'm going to divide that by 23,250. And then what I'll do is I'm going to store this as k. So remember, we hit our little store. It's going to take that. We do alpha k. So there. Now, anytime I hit the k button, that's the number it's going to put in there for me. And I just need to do 18,000. Sorry, 18,000. I need to do 18 and then times e to the 20,000 times k. Oops. Wrong button. There we go. And that's how we got 9.915 or 916 grams. Okay. For the second one, we're going to do the exact same thing, except instead of using 20,000, we're going to use 40,000 for it. So I can actually just go back over here, and we'll just say delete. We'll put in a 40, and that's where we get our next one then as well. So 5.4622. Okay. The last one here, we can say we're going to take 18 e to the kt power equals 5. And you can see I ended up getting 42,965 years. Let's just kind of show you how you could do that. Again, we showed you the graphing way already that was maybe a little bit faster. But we can divide both sides by an 18. That would be our first step. And now I have e to the kt equals 5/18. Then we'll write the natural log of both sides, and we end up getting the natural log. Of course, the natural log with our base e, this just ends up being kt equals ln of 5/18. And then we want to know how long, so we're solving for t, so I'll divide both sides by k. And you can see it comes out a little bit cleaner, a little bit quicker when you do this. I told you in the last one that there's some faster ways of doing it, and that's just using our variables and our notation. So I get t is equal to the natural log of 5/18 divided by k. And remember, k is that really big ugly number that we stored in our calculator. So one last time, let's just go ahead and do this. We're going to say natural log 5 divided by 18, and then we'll take that answer and we'll divide it by k. That's where we get our 42,965. That's it. That's all there is to it. Okay. All right, ladies and gentlemen, I hope that you learned something about half-lives and logarithms. I know it's difficult, or it can be, but you just want to make sure you understand what each number means, whether that means that your starting value, whether it's the ending value, or even just understanding the growth rate and how that means, how that doubling value happens. So always go back and be using your calculator when you can. And I like the graphs. The graphs make things really clear. So make sure you use the graph and the intersect feature. See where your lines run into each other. All right, good luck.